Good morning, everyone. So this is going to be the last lecture. I hope you enjoyed a bit the previous ones. So this is going to be the continuation of what we have seen yesterday on the case where we start adding jump term and regime switching. So I decided to talk about some PDEs at the last lecture, and in particular, how to extend some of the existence results, relax some of the assumptions in the existence results, because those assumptions are not satisfied in the linear quadratic setup. And in the linear quadratic setup, we will be able to find explicitly the solution. So that will give us an idea about how to relax some of the assumptions. So I'll start with the infinite dimensional PDE approach, derive the Bellman equation. Well, I will directly give you the Bellman equation, and then move to the case where we have a common noise, the master equation, including the common noise, and then discuss the linear quadratic case with variance terms, covariance terms this time, and the mean variance approach. And I think I will not have time to discuss the discrete time version, so that will be in the recitation after the lecture. And keep in mind that we will be able to retrieve the continuous time results through a discrete approach. So that's like numerical methods, right? You discretize the system, solve the optimization system in the discrete framework, and then when the step size goes to 0, you retrieve the continuous solution. Okay? In the linear quadratic setup. So that's the agenda for today. So the PDE approach that we are going to use here is the following. We will write the problem as a deterministic problem, although initially the initial formulation is stochastic. So the deterministic object will be the distribution. Okay, you write in probabilistic approach. The distribution is a deterministic object. You solve a Fokker-Planck equation. And then you write the expected value of the cost functional as a function of that object. So that's a deterministic optimal control problem. I mean, game problem, right? Now, for this deterministic optimal control or game problem, you can write down the dynamic programming principle for it. That will give us a Bellman equation subject to the Fokker-Planck equation, but you will not need the Fokker-Planck equation anymore because this is part of the state of the Bellman. Now, when you differentiate that equation, differentiation with respect to measure, you get the master system. Okay, it's a very easy thing without going into finite number of players, getting the limit to infinity to derive the master equation. So here, the master equation will be just the derivative from this infinite dimensional PDE. Okay. So the system is the following. I start with the case without common noise. So the Bellman equation is given by the equation here. V hat is the value function where the state is now M. M is the distribution of the dynamics. Right? M is the probability measure. So that's now our new state. It's infinite dimensional object. V hat will be the value of the optimization problem for player I. And the Hamiltonian now becomes this with some integral terms. Why is that? Why is now the Hamiltonian with an integral? So M is a probability measure. If you want to write down the equation for M, I will do that in the next slide. This solves a Fokker-Planck equation. You integrate by part that equation, right? So when you integrate by part, you get the integral. It comes with an integral form. Right? So that's why you have the it's integrated Hamiltonian, and this to be equal to 0. So this is deterministic object. There is no stochasticity on this one. Now the Hamiltonian is a function of the probability measure. It's a function of this object V hat with respect to M. So this derivative with respect to M in the Gateau sense. It's just directional derivative we are doing here. So Gateau derivative here. This is you first do the derivation with respect to the measure, and then differentiate it with respect to the state, to S. Okay? So first order derivative, second order derivative, I mean, if you want third, because first in M and then twice in S. Okay? So this term because of the drift, this term because of the diffusion. And then you have jump term. So the jumps and the switching involve the value function itself, so this object. The jump term is here. This is the variation of the value when you have a jump size mu. You move from S to S plus mu. Mu is a function of the jump size, time, and switching. This is the value differentiated at M, and this is the first order variation, the same mu that appears here. So this is the jump object, and then the switching has similar structure. Switching means you switch from one dynamical system into another. Okay? So this is your Hamiltonian. The cos is going to be quadratic in our example. So if you have a general cos structure, you put it here. This is the cos functional of player I. Now the drift is the drift that is coming from the state. So remember from yesterday, the dynamics looks like this. Derivative of the state is equal to B. So the B is the drift. It's a function of time, measure, and switching, and so on. And then we have the diffusion term. And then we have a jump term, a common noise in the general setup. And then we have a jump term that has mu and Poisson process. Okay? So this is diffusion, this is common noise, this is jump. And then we have a switching. Okay? We have switching, jump, common noise, diffusion, and drift. Now the drift B is what you are going to put it at some point there. So the drift is going to be here. And then this is multiplied by this measure. You first do the derivative with respect to the measure, and then differentiate with respect to S. And that's the equivalent of your gradient of the value. Right? And this is the second derivative with the diffusion, and then jump and switching. Now, if your diffusion and jump are controlled, means if this is a function of u, then it appears in the gradient, in the minimization framework. Right? So sigma will be a function of the control. And the jump term, the jump size, the jump rates might be controlled. So mu could be a function of the control variable. So that's why the Hamiltonian is more extended. So because you have a control, the control appears in those terms. Okay? So this is the extension of the Hamiltonian. It's not Legendre transform anymore. We are sorry for that. Because when you have u inside the sigma here, by taking the square, you get something quadratic in the control if sigma is linear. But here is different. You are integrating it. Inside you have the control variable. Right? So that's more involved object. Rho I? I is the agent I. We have n players. Other agents are, so there are other agents. They control inside your cost function. You have all the control of all the agents, even the distribution of control of all the agents inside this cost. You do have the same thing here. The drift is, we'll be back to that. So the drift, it's not. Inside the cost, you have all the control of all agents. We'll write the cost. So next slide. Okay. So let's look at here. Linear quadratic setup. The cost has this structure. So you do have I here. Look at the dynamics. You have the control of J's inside. Okay. So I and J are coupled through their control process here. And you have expected value of the control of the other agents here. Okay. So that's why we need to track the I's. It's not the coupled problem. Otherwise, you are back to standard manifold type control. So this is not manifold type control because the dynamics are coupled through all the control of all the agents. Okay? So we want to solve this PDE. So if you look at the assumptions, in particular in the stochastic maximum principle, we are assuming that the cost here, the gradient of the cost, the derivative of the cost is bounded because we are assuming it's Lipschitz and so on. For linear quadratic, this is not satisfied, obviously. So you cannot really apply directly the maximum principle to this problem, although it's just quadratic. But we'll be able to solve the problem explicitly and show that it's optimal. And then we see, okay, how can we relax some of these assumptions like boundedness of the cost functional or boundedness of the derivative of the cost functional? Because the derivative of the cost functional here is linear, so that's not bounded. Right? Same thing for the dynamics. Some of the dynamics, they don't need to be bounded because of the common noise or, so you might have sometimes unboundedness in the coefficient, but still we have optimality. So that's the gap between the existence theory and some of the basic problem that we are solving where we can show optimality without going into, without satisfying some of the assumptions that are required in the existence theory. Okay? So this is the case without common noise. Now let's move to the case with common noise. The jump terms are same as before. The switching terms are same as before, but the Fokker-Planck now is stochastic because I'm adding a common noise on it. Now, if you look at carefully the Fokker-Planck, so D is for drift. So this part is same as before. Sigma is for noise. Sigma naught is for the common noise diffusion coefficient. So the derivative. So this part is almost the same as before, because I had two Brownians, so it makes sense to have the sum of the diffusion coefficients here squared. But this is, so you get this by just Ito's formula. So you have the common noise free object. Now you are just adding a Brownian motion. You do Ito's formula to that part only, and then you get this term. So you see that Ito's formula in the martingale part has a derivative with respect to the function you are applying. So that's to get a derivative with respect to S. So it's a derivative of your density, if you prefer. That appears there. Okay, if you have very smooth data, then you are lucky. There might be a density, and you could differentiate with respect to S. Otherwise, this becomes more tricky thing, because you get vanishing object and so on. So in the linear quadratic, since we understand what is going on, we know this thing, and we show that this is not going to vanish. It will help us in regularizing the solution. But if you are more involved Hamiltonians, I have no idea about if we have strict positivity on this part. Okay. The Bellman equation is also modified. It's going to be stochastic with the correction term on it. So the correction term is, which one is the correction term? So this is the standard. This is standard in the Bellman. This was same as the previous one. So there is nothing new in this part. Why do we have extra? So there is a Brownian motion term here. This comes from this part here. Okay? We are just applying Ito's formula. So this is the same as this thing applied to V. Now, why do we have this term and this term? Second derivative with respect to the measure. You differentiate V twice. Because M is our state. Our state now has a diffusion component. So second derivative makes sense with respect to M. So that's why you do have this term. That's your Asian, if you prefer, with respect to the measure. But it doesn't say why you have this other term. So that's the correction term. Okay? So if you have a backward SDE, the correction term is the one that makes you adapted to the filtration you are running. If you are more familiar with YZ in the classical notations, so this is the correction term coming from the backward SDE. So now we couple these two, and you have your mean-field game system with common noise, with jump terms and switching terms. So in your setup, you don't have this part because you don't have a jump term and switching term. But once you have a jump term and switching term, V, with respect to the measure, is involved. So far, we have seen only cases where it just depends on the derivative and the second derivative here, but not on V itself. So the V and the integral, this comes because of the jump and the switching. Okay? So this is what we want to understand. If you want to solve the applications areas, this is the problem we want to solve. Without this part, this is just for quadratic. I replace this by the terminal object. But the rest of the equations are general. Okay? We want to solve this system. This is the situation without constraint. So I'm not involving any constraint. If you want to add constraint, the constraint goes, constraint in the control goes in the optimization of the Hamiltonian. That brings other difficulties on it. Okay? So the Hamiltonian, as I said, for this problem, becomes the general Hamiltonian is this object here, where the running cost goes here, depends on the control of player I, but also the control of the other players. They are inside this cost function. The mean field appears in that cost if you prefer to include it on it. In the drift, you have the state, you have the mean field object inside, and you have the control action of all the agents inside this drift. Okay. So they are coupled through ear and ear. Now, derivative with respect to M, as I said, is just we are doing directional derivative here. We are not using any lifting thing because in the lifting approach, we need to identify the lifting operator. So that's why we just differentiate it, do the variation, and identify directly as a direct method. So we identify the lifting operator. That's why I'm using the directional derivative here. And then differentiate with respect to S to get the lifting function. Okay? This is just direct, brute force. Okay? Because at some point I need to calculate it. So is there any function that lifts it? Okay, that's fine, but I need to identify it. For that, I use directional derivative. So the diffusion, in my previous example, mu was independent on the control. We will make it now dependent on the control. Okay? The control will enter into this function here, mu. Control of all the agents will appear there. And in the switching, the equivalent will be kappa. That will enter, the control will be appearing there as well. Linear one. Okay? And we'll be able to solve this PDE for the linear quadratic case. Beyond it, it's more involved. I have no idea. So linear quadratic case, the cost functional, as I said, becomes this. So quadratic, S is the state, S hat is the conditional state with respect to the Brownian motion, the common noise, S hat square here. I write in this form because you can see the variance. If you have the expected value version, you see the variance of the state, conditional variance of the state, conditional variance of the control appearing there. And so we want to minimize this first, find the optimal control, and check if our ansatz solve this PDE. This is what we have been doing from the beginning. But I didn't present the PDE. Now you have the PDE. If you prefer this way, you have this PDE, plug your ansatz here and see if it's solved. And you will get the same equation, I promise, because we have checked it and that's in the paper. So how do we move from the PDE I have given you to the master system? Why master system instead of master one equation? It's because now we have multiple interacting agents. You get a system of PDEs. We are back to the standard. It's systems of PDEs. That's why you get a master system. How do you get it? just go back to the previous PD, differentiated with respect to measure and with respect to the state, you get the master system. The same master system that was derived in Minfield games. I'm not going to write that. And this part with the Minfield type control was done by Professor Ben Susan, if you want to check the case saying that the two master systems are identical for Minfield game problems. For Minfield type game problems, they are of course different because of the variation with respect to the measure. As we do in maximum principle, the two are different. Because one is solving optimization problem with variation with respect to, is controlling the measure, and the other doesn't. You freeze the measure in the other one. Okay. So let's look at it. I'm going to jump on the Pondrayagin part. That was part of the lecture last year. If you want to have more details on it, it's in the website. The videos of last year are online. Let's go to the example. So the cost function, you remember these equations now from the first day. We wanted to solve this complete case, complete linear quadratic case, where we have a quadratic in the state, quadratic in the value, in the expected value of the state, but then we add a linear term. This is to include linear mean variance type of things that exist in the finance literature, for example. We want to maximize our revenue, but at the same time, we don't want to risk on it. We want to reduce the variance. So one approach is the mean variance approach. That's some kind of scalarization. This is two-level objective optimization, but that's more involved because the solution will be Pareto optimality. We don't want that. We want a scalarization technique, means transform this into single objective optimization. That will lead to mean variance minimization or maximization problem. So this includes the mean variance framework because of the linear term here and the quadratic term here. Okay. Now, the running cost involve similar structure as the terminal one, but also include covariance. If you combine these two, you get the covariance of this between the state and the control, and linear term in the state and the control. Okay. What is missing is constant term. Well, if it's constant, you don't add to the cost. Okay. Now, the state dynamics. Now I'm adding constant term. I mean, constant, but it could be a function of time. Okay, and dependent on state. I mean, okay. So constant term. And then linear term in the state, linear term in the expected value of the state, linear term in the control, linear in the expected value of the control. So this time they are all there. The coefficients could be switching dependent, because then it will allow you to move to this dynamical system to another dynamical system. Okay? Same thing for the diffusion and same for the jump term. So this time they are control dependent. The coefficient of the jumps are control dependent. And this is something that you see immediately when you do investment over several options, several assets. You have seen in the example yesterday that the control, the diffusion coefficient and the jump coefficients depends on the control, because you need to decide how much money you invest here and there. So your control appears there. It's not just something that we create there just for our math, but it's because in the application, the control were appearing in those type of noises. Okay? Now, to solve this PDE, to solve this problem, I will use the previous PDE. I was able to solve, remember, without using the PDE. And then we will need to compare the two solutions, and it turns out that they will be identical. So who is ready to go over the PDEs with that? this term here in the diffusion, you get sigma square. You need to have the square of this that will appear. And expand it, so you are looking for uj's, and the square of that will appear in your PDE. And you need to optimize with those. So you get a ratio between the gradient and the second derivative. So optimal u will be a function of that ratio that will appear. Okay? So the optimal control will not be just the gradient of v. It will be a function of that ratio. First, we transform the problem this way. We write in the variance form so that you can see that actually the variance appears there. If you prefer the variance than the other term, you can choose them such that this term disappears, but then you have only the variance reduction problem. But in the general setup, you might have covariance involved on it. Now, if you set your epsilons to 0, you are back to, you will have without these terms and so on. So this is more convenient thing. So you have the general setup, and for your specific application like mean variance or variance reduction problem, you can identify the proper coefficients. That's the reformulation. It doesn't change the problem. It's just rewriting the same thing. Now, solution. For those who are interested in the PDE, plug it there and with that ansat. And the ansat is the same as yesterday, the same ansat. But now, since I have a switching in the dynamics, the coefficient depends on time and switching. Okay? So that's the switching state where you started, S tilde naught, because S is the state. Now, S tilde is the switching, the regime where you are. So this coefficient alpha I times the variance term, the conditional variance term. The beta, similar, same ansat as yesterday. Okay? You take that ansat and plug in your PDE. And you'll have equations for the alpha, beta, gamma, and delta. I mean the PDE after doing the optimization. Okay? Yeah. The optimal control will have similar structure as yesterday, but there is a small difference. So here is not alpha anymore. You will have another function that involves all the alphas of all the players because they are interactive. So it makes sense that your control is not independent on the others. It's not just a function of the state. It involves coefficients that are deterministic, but involve that are solved by other agents, if you will. Right? That's because of interaction. In the optimal control case, you don't have that because there is only one decision maker that is doing that. You plug all the controls together and you are optimizing. So this does not involve the coefficients of the others. Now, what will be this tau? I will give you that in the next slides. The coefficients. So alpha will be a function of time and switching regime. Remember that. So this is when you are at the regime S tilde, you get this ODE for alpha. Okay. This term and this term were appearing even in the deterministic game case. So that's not any difference. This is because your diffusion is state dependent. In your diffusion, you have the state. Okay? Because of that, you get this. This is because your jump is state dependent. Okay? This is because you have a switching in your model. If there is no switching, this term disappears because you have only one single switching regime, so there is no change here. This is 0, and this term disappears. Now, this is because you are control dependent in your diffusion. Your diffusion is controlled. This one is because your jump is controlled. These other terms, cross terms, they disappear when your diffusion are uncontrolled or without state. And this was already in the deterministic case. This one, I don't know where it comes from. It's just for some calculations it appeared, okay? No, I think it appears in the deterministic case. This one appears in the deterministic case. Okay? So that's for alpha, only alpha, okay? Now we'll need to write the equation for beta, and then the equation for gamma, and then the equation for delta. So in the equation for alpha, in the deterministic case, this one was alpha j. The tau j was alpha j. Now it's interactive term, as I told you. This alpha is a backward ODE. Everything here, there is no state in it. This is just a deterministic object. It's function of your data, of the coefficients. You could solve this offline. I give you the coefficient, I give you the model, and you run this offline because it's independent on the state. All right? The alpha is a backward ODE, so the terminal, at the terminal time, we will give you that Q. Q is given to you. And then you solve this ODE. If you are more fan of ODEs instead of PDEs, this is for you. Okay? But backward ODE. You need to show that this ODE has a solution that is positive. Okay, has a solution around capital T that's free. That's free from Cauchy's, even backward Cauchy, but whatever. Terminal value. So around capital T, there is a solution. It's completely trivial thing. It's linear up to somewhere, and it's not linear year and year. So it's C1 around the terminal thing. So there is a solution around capital T. But it doesn't tell you that it will not blow up. Okay? When this tau is linear, then you get a linear in alpha, then you get quadratic one. Then it's Riccati equation. The Riccati equations are relatively well understood now. But if this one is not linear, then it's not Riccati anymore. So you have to restudy the entire thing here and show that it has a positive solution between 0 and capital T. But we are going to, we are studying only the linear quadratic, and this term is going to be linear. Okay? We are lucky. The nonlinear version of it, by the way, is in the lecture last year. Show that there is a positive solution to it. It's part of the lecture last year. Now, beta. So beta is similar. So this beta does not appear if you don't have any mean field in your problem. You will have only the alphas. Okay? So beta is really because of the mean field problem. You see B bar. So everything that is bar is because of the mean field. Okay? Sigma bar appears there. Mu bar appears there. So this is because you are state dependent in the diffusion and in the jumps. Same thing. This is because of the switching. This is because of the control dependent diffusion. This is because the jump is dependent on the control. This part is because you have state dependent on the structure. This is coming from deterministic, and the final value is given to you. Okay? Another Riccati equation, right? Conditions for having positivity, as I said, this is 1D, okay? People have done for matrix valued stuffs, even with operators and so on, but this is 1D. In 1D, the Riccatis are much easier to handle than the 2 or more, the matrix version. So I'm saying positivity of these things. In the matrix thing, it says the entire matrix is positive and so on. It's more involved. You need to go and check all the eigenvalues and show that they are positive. And I'm not going to do that here because I have a real number. Another more complicated equation. That's for gamma. Okay, this tracks all the terms that are linear. I think I don't know all the terms, but this is because of the jump. That's probably obvious, the obvious one. The epsilons there were tracking the linear terms. So this will appear even in the linear, even in the deterministic case. This term, and this term will appear in the deterministic case. If you look at in the example of in the recitation, you had those terms all already. So this equation is much simpler than the previous one because you don't have the quadratic term. So this is just linear ODE. You are linear. Just integrate it, you get your solution. So no positivity condition for this because you don't need that. You need positivity for alpha. Okay? And then delta. Delta is the one that gives you the real cost. So this does not require any condition. If you know the previous ones, this is free. It's just if you want to get the cost, this is important, but not for the control. If you want the value of the cost, delta is important for that. Okay. Now, I will tell you what is the tau, the coupling. So I told you that it's linear. The coupling solves this equation. Matrix A times tau equal to V, where A is given below here, and V is here. So because of that, you get a linear structure. Because of this, you just need to invert this matrix. Now, is that matrix invertible? Is another question, right? What is the condition? So the diagonals are 1, which is good news. And then the off diagonals are here. It means that if I'm noise free, if I'm diffusion free or jump free, it's just identity matrix. So you could say that, okay, if those are small, it's also invertible, right? Yeah. It's just a variation from the identity. So you'll put a condition on the invertibility of this, saying that the determinant of this is non-zero, whatever you prefer. But around capital T, this matrix is invertible. Okay. And then you get you do the same thing for tau bar with V bar, and V bar is given here, and the A bar is also similar to the A because it's 1 in the diagonal, and in the off diagonal you have this terms. Okay. So you invert this matrix A, and here you get a tau, and that tau is the one that was involved in the equation, in the previous equation. And there are coefficients that were appearing, Ci, Cj's. Ci is given here. We need this coefficient to be positive. Okay, good news, Ri was assumed to be positive. This was part of the data. Ri is the coefficient behind U squared. So positive because we are minimizing. So if this is positive, then the rest, I have no idea if it's positive, but if I ask alpha to be positive, then I'm done. That's why the condition is alpha to be positive. I need to show that my ODE has a positive solution. Okay? So you need to show that this alpha that is multiplying here is positive. If you have the positive alpha, you get strictly convex. Fine. You don't need to check any other thing because it's coercive because it's going to infinity. Right? So I have something that is coercive, that is strictly convex. I am happy. There is a unique solution to my best response. Because I'm assuming that there is no constraint in the optimal control. If I impose constraint on it, it will be more involved because I don't want to. So this is unconstrained case. Okay. Now C bar, we need to do the same work for C bar. C bar has to be positive as well. So for that, this term is the one that we get. So this is near the U bar square, the R bar. So this is positive from the data. If I show that alpha is positive, I'm done. So same condition is used there as well. So alpha to be positive, this is the main thing that we have to prove. Okay? Again, I know that there is a solution to the problem from the beginning because I assume that data are positive. I'm minimizing strictly convex function. That is coercive. Okay? So I will briefly comment on the discrete time and then leave that for the recitation. So the main idea is this. We want to solve the same problem but in discrete time.
Before we go to discrete time, I have a question. When you have common noise back in the setup, does the linear quadratic setup give you that the dynamics of the distribution that's consistent with optimization ends up coming out Gaussian or something?
Yeah.
Does it work with the jump process without like assumptions like symmetry or something?
Finite number. We checked only finite number of jumps. And in the finite number of jumps, the coefficient, the rates of the jumps, so the jump process was the jump, you mean Poisson jump or switching? Because these are two jumps. Okay, the switching, we are considering finite number of switching regimes. So it is, the Poisson is relatively general. We want the rate to be L2 with respect to the, here is the condition. We are assuming that the mu is the rate functional. Nu is the intensity measure. We want this to be finite. This is standard condition. Because we are doing L2 quadratic problem, so we are asking all the objects to be finite, to have finite second moment, which is a reasonable fit. If they are infinite, you are just minimizing something that is already infinite. Okay? That's the only condition in it. That's why I considered random measures for my nu. These are sigma finite measures. I don't have to deal with infinite or Cauchy distributions or whatever your favorite is. I don't have to deal with that. What do you mean symmetric? Your state, there is only one state. The state go up or down with a certain value. I have one state, that is S. You, from that position where you are, you jump somewhere, or you go down or up with a certain rate. I don't have two states. If you have two states, you could involve several jump stuffs, but I have only one state. It's just S. So you can look at asymmetry when you have S1, S2, and different jumps for each. You could do that. But I didn't look at it. Yeah? Do you have a question on this? So for the, let me comment on the, discrete time case. So what we are going to do is time is going to be discrete now. With the step size that is fixed, delta. The cost functional is the same as before. The dynamics is the same as before. But more involved in terms of processes. We don't need to be Poisson or Gaussian, because in the discrete case, you could solve for more general processes. That is finite second moment. But I will choose to be difference martingales to compare with the continuous time framework. Okay? So I'm going to discretize B to be like B plus delta minus BT. This type of term will appear. Okay? And then I solve the discrete time problem. Look at it when delta goes to 0. And I want to check if I get the same solution as the continuous problem. Okay. In this case, I was able to solve explicitly the the problem, it was much easier. Okay? And this explicit solution will be more detailed in the recitation. So to solve the discrete, we are not using the Bellman equation. We are using Shapley's operator for games. Dynamic programming is much easier in the discrete. You just say, okay, your value function now, so will be a function of what you are getting now and your future payoff. Future means expected value with the value in the future state. That's your Bellman operator in the discrete. And in the game context, this was done by Shapley, and that's called the Bellman-Shapley operator. We use that. And then we apply with the guess functional again and identify the coefficients. So there is a direct method version of it where you don't need any Bellman to it. You just write a telescopic formula, which is the, where do we have any? You can just reverse it. Here we go. So you write this way. Your functional at time k is your functional where you start, somewhere, 0. And then summation from k equal to 0 to, well, not k, another term, t equal to 0 to k, or to k minus 1. Let me put k minus 1. Okay, k is more than 1, okay? Then you put here ft plus 1 minus ft. You don't need Ito's formula, you need only this. Your Ito's formula is replaced by this. You don't know all the complicated things. Okay, that's my new Ito's formula for discrete. I only use this to solve the problem. Nothing else. Okay, now I'm going to take a guess of f that has a quadratic structure and run this thing, because my problem was quadratic. Okay? And then derive equations for the coefficients. So in the discrete case, you will have terminal value, and you run those discrete difference equations backwardly, and you get your coefficients, and then you get explicit form. Much, much easier. But when t goes to, when delta is the step size, when delta goes to 0, you get the continuous time equations. So you get the same solution as the continuous time problem. So this is helpful for numerics at least. You could say, okay, I discretize my problem, then I solve a discrete game problem, and I want to know if when those parameters goes to 0, I get the same situation as the continuous. If this is the case, then your numerics are working. If not, you need to ask a question for your numerics. So this says that we are really solving, even numerically, the same problem. Okay? So I will leave the details of this to the recitation part and open the audience for questions, discussions. No, I want to ask them questions. Any question? For the master? Yeah. Yes. The explicit solution for the master is the one that I will. For the linear quadratic, yes. 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 So this is one of the cases where the master equation is solved explicitly with the common noise and switching and jump. Yeah, so if you go beyond, so you will have this, it's still infinite dimensional PDE, remember that. I don't know how to reduce this to a finite dimension. So initially I said, okay, I need only the mean in my problem. So I want to write a dynamics for mean and make it two-dimensional. Here is the mean, here is my state, couple them and write dynamic programming on it. It turns out this doesn't work. You need to write the infinite dimensional thing to solve a finite dimensional problem. There is a trick there somewhere. But in the maximum principle, it's finite dimension. Because I differentiate on this thing, I can identify everything as a function of the average. So it's finite dimension, the maximum principle, because the maximum principle is the derivative of this infinite dimension. So maybe there is a question that people can look at. It's a finite dimensional version of the Bellman equation for this problem, instead of the infinite dimensional PDE. I mean, the problem is second moment problem. So why do I need the entire distribution for it? It's something that we should address, right? So other cases, we are able to, it's not only quadratic, we are able to extend to things like that, and things like that, and things like that. You have seen logarithm of the control yesterday in the consumption, and the solution was explicit. Logarithm of the states, or something into the power alpha. So this is in the lecture last year, explicit solution to it. So we can do some nonlinearities sometime. So the question is open. If we can continue extending this direct method, this gives another way to check our complicated PDEs, because we will have those explicit solutions. We enter there and say, okay, solution should be this way or that way. So that's the idea. Start with the linear quadratic, extend it, and then this gives an array about the solution of our PDEs. Okay? With jumps, switching, common noise.
Let's thank Hamilton for his nice lecture.